Hello everyone. In this video, I'm going to work through an example showing you the process of validating arguments based on symbolic logic. Now, by validation, we mean whether the argument or whether the conclusion that we have drawn from a set of given statements or what's called premises is a valid argument. That means if it is a correct conclusion we have drawn from the given premises, or whether there's a fallacy in that conclusion, in that argument. So let's first go through the example that we will be working on. We have here the first statement given to us as we will go for a bike ride or we will go shopping. And then the second statement is we will not go shopping, therefore we will go for a bike ride. So in this entire construction of the argument, we see there are multiple parts, right? The first two statements are called the premise. All right, so there are two premises, premise 1 and premise 2, 1 and 2. And then below that is the argument. So this is the argument or the conclusion that's been drawn from the two premises given above. So this is the construction of any argument. Now, the first step in the process of validation is to represent this entire argument in symbolic notation. And for that, we are going to go step by step through each statement. So we'll take the first premise, we will go for a bike ride or we will go shopping, and then break it up into two simple statements to represent them with symbols P and Q. All right. So in the first premise, we have two statements, two simple statements connected by the disjunction connective, the or statement, correct? So I'm going to write here P, and that's going to represent or that's going to denote the first part of this compound statement. We will go for a bike ride. We will go for a bike ride. And then we will have Q representing the second part of the statement, which is we will go shopping. We will go shopping. All right. So now let's represent the entire premise 1 in symbolic notation. So P, there's going to be P. We will go for a bike ride. This is P. And then we have the or connective that's represented by the V symbol. And then we will go shopping is Q. So we are going to have P or Q. So that represents the first statement, the first premise, this first premise, all right? And then we have the second statement or the second premise, which says we will not go shopping. So we will go shopping is Q, but there's a negation in the second statement, a not statement. So that is represented by the tilde symbol. So we are going to write that as not Q. All right. So the second statement or the second premise is represented in symbolic notation as not Q, tilde Q. And now let's look at how we can represent the argument. It says, therefore, we will go for a bike ride. Now, therefore is represented by this triangular set of dots. Therefore, we will go for a bike ride is P. So therefore, P. All right. So this is the entire argument written in symbolic notation. Now the next step is to build a truth table for this entire argument. However, before we go about doing that, we first have to string all these statements in symbolic notation, the premises as well as the argument, into a single conditional statement. All right. Now the first two premises are going to be connected by the and connective, right? By the conjunction. So the way we are going to write it is if P or Q and, all right, so these two premises are going to be connected by the and symbol. So and not Q, and I'm going to surround this entire if condition with square brackets, then P, which is the argument. All right, so if P or Q and not Q, so given both these premises, then the argument P. So now we are ready to go about and build a truth table for this entire conditional statement. So we are going to build the truth table column by column. But first of all, how is the truth table going to tell us whether the argument is valid or not? The way we will know that the argument is valid is by looking at the final column of the truth table. If all the truth values in that final column are true, then that means it's a tautology, and therefore that will confirm that the argument is valid. So let's start by listing the combinations of true and false for two statements, the P and Q. That's what we are working with here. So in the first column, I'm going to have P. In the next column, I'm going to have Q. And then I'm going to list all combinations of true and false. Recall that the number of combinations for two statements is going to be 4, 2 to the power n, n being the number of statements we are using to build the table. So we are going to first begin by representing Q, or listing the values, the combinations for Q as TF, TF, and then for P it's going to be TT, FF. All right, so this gives us all possible combinations of true and false for P and Q. So we could have true, true, then followed by true and false, and or false and true, and then finally both can be false. All right, so given these combinations, let's go on to setting up the table or the columns of the table using this statement. All right, so I'm going to write it as P or Q. All right, surround that by brackets, and then the and followed by not Q, and all this has to be evaluated step by step, and then this conditional followed by P. All right, so what do we do first? We have to evaluate P or Q, the innermost brackets, correct? So I'm going to rewrite all these combinations: true, true, false, false for P, and TF, TF for Q, and then I'm going to evaluate the truth values based on the or connective. All right, so true and true, or rather true or true, is going to give us a true, true, and let's use a different color this time. All right, true, and then true or false is going to give us a true, false or true is going to give us a true, and false is the only case where the or returns a false, correct? So we've evaluated this innermost bracket. Now we go outside the round brackets to not Q. So this is easy because all we do is negate the Q values. So it's going to be false, all right, false, and then true, false, true. All right, so now that the negation is completed, we have to evaluate the conjunction, which is the and. All right, this is what we are evaluating at this point. So I'm going to use a different color here. So which columns are we looking at? We are looking at this column here under the or and the negation, right? And then we are going to evaluate the truth values for and of these two columns. So let's do that. Here it's going to be true and false returns a false, correct? It should return a false. True and true returns a true. True and false returns a false, and false and true returns a false. All right. Now we have completed everything inside the square brackets. We have to now evaluate the conditional. So what are we looking at here? I'm going to use a different color to highlight the rows that we are looking at. So we are going to this time look at this row. All right, take into account this and followed by P. So these two columns are what we are going to now evaluate, but let's list the values for P at this point, right? So P was true, true, and false, false. So now we go ahead and determine I'm trying to find another color. So this is what we need to fill out, and this is going to be our final column. All right, a final column that will tell us whether the argument is valid or not. So again, this is a conditional if truth table that we are trying to come up with truth values. And the only time that a conditional will return a false is when the if condition is a true, but the then condition is a false. All right. So let's go one by one here. False and true should return a true, right? True and true should return a true. False and false should return a true. False and false should return a true. So here we see this was the final column of the truth table that we worked on. This entire column of values is true, correct? So that makes this statement or this argument a tautology, and the conclusion should be that it's a valid argument. It's a valid argument. All right, so this is the step-by-step process of determining whether an argument is valid or if there's a fallacy in it. So if there was even one truth value in this column, which was an F, which was a false, then it would make it an invalid argument. However, we have all four truths for each of these cases. Therefore, the conclusion is it's a valid argument.